Hi, I'm Iago Suarez and I'm presenting GlueStick, a joint work with Remy Pautrat, Jim Fan Yu, Mark Polyface and Victor Larson. Image matching is a fundamental task in computer vision that given a certain point in one image is able to find it in the other image as the yellow examples that we can see here. Typical methods use correspondences between key points describing its surrounding texture. However, sometimes matching can be very hard because of the lack of texture, drastic lighting, viewpoint changes, or repeatability. And to solve this, we leverage line segments. However, line segments come with their own problems. Namely, they are harder to match because their texture is not that good, they can be easily occluded, or their endpoints are unclear. But in last years, new matchers has been proposed to match points using not only its visual appearance, but also the geometric information. And geometry has been used to match lines, but only in handcrafted and error-prone ways. So in the following, we will pick the best of each to create GlueStick. The main idea behind GlueStick is to join the point and line matching that was done separately and glue them together. Also, unlike handcrafted methods, we do it in a data-driven approach. We start with two input images. We extract dense descriptors and key points using a CNN and lines using a classical method. Next, we combine them into a wireframe, where we merge line endpoints and key points that are close. They constitute the nodes of our wireframe, and the lines are the edges. And then we have to match wireframes from both images. We will do so with a graph neural network that sends messages from one node to the other based on attention and connectivity. The GNN is composed by three types of layers: node self-attention, line message passing, and node cross-attention. We begin by adding a positional encoding to each node and edge of the wireframe. The second one will encode location, length, and direction of the edge. Let's build the graph in this way. Let's assume that these are the features in our graph, and we will focus then in node self-attention for this specific node. In node self-attention, we use attention from all the other nodes in the same image to create the message that is going to be propagated. And then an MLP takes care of processing this message with the current node feature and generates the new feature for the next layer. The next step is line message passing, which is a novel contribution in our paper. We use the connectivity of the graph to collect information from connected nodes. Here we take the current node feature, its neighboring features, and to consider the line direction, we also inject the edge positional encoding for each edges arriving in the actual node. We concatenate all this information passing through another MLP, and we average the information result for the different edges to produce the final message that is aggregated into the feature of the current node. Last, we use cross-attention layers that are very similar to self-attention layers, but instead of attending to the current image, each node attends to all the other nodes in the other image. After the GNN, we use two assignation matrices, one for points and one for lines. In the one for lines, we have to disambiguate between this correct option and this incorrect one. We do so by comparing the similarity of the endpoints for each possible line match. As you can see in this plot, GlueStick largely surpasses all the previous line matchers and provides boosted performance when applied in post-estimation problems. Let's see some qualitative examples. Here we draw points and lines matched with GlueStick. Each correspondence has the same color in both images. Our method provides stable matches, robust to repetitive structures and viewpoint changes. In conclusion, when matched together in a wireframe, lines and points can help each other, boosting the results of downstream tasks. Thank you very much for listening and see you in ICCV.